Today we have here Professor Andrew Pritz from the Department of Computer Science at the University of Cambridge, who is here to talk about the programming language semantics. And we're very glad to have him today. With that said, I will just pass the floor to him. And again, thanks for accepting this invitation. It's a pleasure to have you.
Thank you very much. Well, okay, so I'm conscious that your, the audience is mostly philosophers and mathematicians, not computer scientists. So I'm going to be telling you about a branch of theoretical computer science, and I'll relate it. I suppose you're going to get a relationship to logic, at least. I don't think I'm going to manage really very much on the mind or AI. You're just going to get my mind rather than anything else. So we're going to be talking, I'm going to talk today about part of what's called theoretical computer science. And I think most people, when thinking of that subject, would think in terms, first of all, of the foundations of computing. I mean, going back to the seminal work of Alan Turing and Alonzo Church in the 1930s, formulating a mathematical definition of what computation is. And following on from that, once you've got that, of course, you can consider questions of feasibility. How much time or space does it take to actually carry out certain kinds of computation? And that's the topic of complexity, computational complexity theory, and the study of algorithms. And that those two things are if you met a man in the street and said that you were doing theoretical computer science, especially I think probably in North America, they would mostly think that you were working on those things. But actually today I'm going to be talking about another aspect of theoretical computer science, which is to do with the meaning of computation, and within that also what is the mathematical structure that we need in order to describe various kinds of computation. So this is semantics, but not semantics of natural language, but semantics of formal languages and programming languages in particular. So I want to tell you really in, I hope, a fairly high level way, without sort of burdening you with technicalities, what kind of thing people have done and latterly are doing in this area of semantics. So we're going to be talking about semantics of programming languages. I don't know whether you program. I'm sure many of you have written programs, and you're probably aware that there are very many different programming languages by now. I've put up here a quote from way back in the beginning of this subject in the 1960s, 1964, in fact, from somebody called Christopher Strachey. So he was I guess a student of Alan Turing, if I remember correctly, but one of the founding fathers of the foundations of programming languages and their semantics. And the quote here says that his definition of a programming language is a large body of somewhat arbitrary mathematical notation introduced in the hope of making a problem of controlling computing machines somewhat simpler. So I think that the interesting thing about that is that at the time people thought of programming languages mostly from a syntactic point of view, so mathematical notation. But it soon became clear that you can't really make progress in developing programming languages and applying them unless you go beyond just the mere syntax of the language and think about it, the underlying meaning in terms of various mathematical constructs. And very much has been done in that area, actually, from Christopher Strachey in the 60s onwards. And actually, in fact, the subject, I mean, one that's was developed in the UK, actually, in fact, in the early days. So Peter Landin, Tony Hoare, Dana Scott in Oxford, Robin Milner and Gordon Plotkin in Edinburgh. These were people who founded the subject through the 1970s and 80s and now into this century. So I'm going to tell you, first of all, what programming language semantics is for. In other words, why should one want to study it? And then I'll talk a little bit about what it actually is in terms of what people have devised in order in the kinds of mathematics and logic that have been used to describe semantics. So let me begin by just trying to motivate why one should be interested in the semantics of programming languages. Hang on a moment. My screen's gone blank. Oh no. Well, maybe you've seen screens like this before. Sometimes your software, your programming language and the program that you've written has bugs, and the bugs are bad enough that they bring down the whole operating system. And you see a blue screen of death, as it's sometimes called. Here is one. So we would really like to avoid that. Here's a quote from Bill Gates, the founder of Microsoft from the early part of this century, saying that software verification, in other words, proving properties of software, proving that your software doesn't have a bug in it that will bring down the whole operating system, for example, is the holy grail of computer science. And at the time that Bill Gates was writing this quote, Microsoft were putting a lot of resource into so-called device driver verification. So writing tools that could carry out formal proofs about the software in which device drivers were written, in order basically to hugely increase the reliability of those device drivers and avoid the blue screen of death. So software verification is certainly a huge motivation, a practical motivation for programming language semantics. And it might be that one wants to avoid the kind of frequent but annoying bugs that they don't kill you, but they might lose you money or just be very irritating. But of course, there are bugs in software which are of a different quality entirely, where the bug in the software actually does kill people or cause catastrophic accidents. So the photo on the right there is the EU Ariane rocket exploding on launch because of a software bug. So software is everywhere, obviously. I mean, it's these days, a huge part of the infrastructure around the world depends on software. And you can't have software without it being written in a programming language. And programming language semantics, in other words, giving a precise meaning to programs written in some particular programming language, is the crucial first step if you're going to produce rigorous methods for proving the correctness of software or proving things about maybe their security, for example. So there's a very big motivation for semantics coming from the subject of program verification. Actually, that's not the only reason why one wants to study it. Actually, writing implementations of programming languages, in other words, the compilers and the interpreters that execute programs for a particular language, very much depends on having a good grasp of, obviously, the semantics of the language that you're trying to implement. So on this slide, I've given a quote from my colleague, Simon Peyton-Jones. So he's, apart from many other things, one of the authors of the Haskell functional programming language. And in that language, you program by basically writing a series of definitions of functions, to put it rather more simply than's actually true, and naively executing those functional definitions could be very inefficient indeed. So the Haskell compiler tries very hard to optimize your code as it translates it into lower level instructions for your actual computer to execute. And as Simon says in this quote, that optimization can be quite delicate and difficult to understand. And without a formal mathematical semantics of the language, you really are hanging by a thread as to know whether what one is doing is actually correct or not, leaving aside whether it actually produces things with good performance. And then there's a third, even more high-level reason why we need programming language semantics, and that's because people do design new programming languages. So programming languages are always being developed because people realize that there's a particular kind of programming application where existing languages aren't very convenient, and so they design new ones, maybe by combining ideas from existing languages in new ways. So I put here a quote from John Reynolds, the late John Reynolds, who was a seminal figure in the theory of programming languages. And what he says here is that one of the reasons why it's so difficult to design programming languages is because naively you might think that you could just combine various features that you're interested in, but when you do that, you get very often unexpected and counterintuitive interactions between those features, and at that point, if you don't have a rigorous definition of what the language means, in other words, its semantics, then you're really not going to understand what one's doing. So that's again one of the primary motivations for studying semantics. So that's why we do it. There are strong motivations from verification, from implementation of languages, and from the design of languages for wanting to have a semantics. Now I want to turn to the various means that people have devised in order to describe the meaning of programs in various kinds of programming languages. In other words, what it is. And I would single out three somewhat different styles of doing programming language semantics: program logics, operational semantics, and denotational semantics. So I want to tell you a little bit about these three different approaches. So I'm not going to really give any details of any of them, but I just want to sort of convey the flavor and the differences between the three approaches, and let's see whether I can manage to do that. So let's start with program logics. So the focus there, and it's the one which sort of most obviously connects with mathematical logic, I suppose, is that ultimately for software verification in particular, we want to be able to prove properties of our programs rather than just testing a piece of software to see whether it does the right thing. I mean, most pieces of software you would have to do an infinite number of tests in order to cover all possible cases of use. So different approaches to actually construct a proof in some kind of logic that under all possible inputs or circumstances the program behaves properly. So describing semantics through devising a logic of programs is perhaps quite a natural thing to do. And just to give you an early example of what that might look like, I mean, if we think about a programming language where the purpose of a program is to mutate the memory of in your computer. Okay, so we might have commands that increment or decrement numbers stored in memory, carry out other kind of instructions and so forth. So that's what I mean by a command. So the Floyd-Hoare logic for partial correctness, that the assertions in the logic look like this symbolically. So C is a piece of program, something that you can execute that is going to affect the state of memory in your computer. And the P and the Q are assertions in some language that describe properties of memory. And this partial correctness assertion is supposed to be capturing the idea that if the memory satisfies property P when you start executing C, and if C actually does terminate, then the memory that you get satisfies property Q. So it's called partial correctness because this assertion is not saying that the command C does terminate when you start with a memory satisfying P, but just that if it does, then the final state will be Q. So Floyd-Hoare logic goes about axiomatizing properties of commands in some language by writing down a series of axioms and rules for generating valid instances of this kind of partial correctness assertion. Let me just give you a simple example of that. We might very well have a command whose structure is a while loop. So this is a command that says while some Boolean condition B is true, repeatedly carry out the command C. So do that over and over again, C until the Boolean condition becomes false. So we can kind of capture what the meaning of that while loop is in terms of this rule that says the following. If we already know that we have this partial correctness statement at the top, so this says that there's some property P, which if it holds and also the Boolean condition holds when you start executing C, then P still holds of the memory when C terminates, if it does terminate. So P is like an invariant property of the memory that doesn't change as you execute the command C. So if we know that partial correctness statement, this rule says then that we can deduce a partial correctness property of the while loop that says that if the invariant P holds to begin with, if we execute the while loop, if it does terminate, then we'll still know that P holds, because every time we do a command C, we keep the property P, but we'll also know that the Boolean condition doesn't hold. In other words, not B is now true of the memory, because we only terminate with a while loop when the Boolean condition becomes false. At that point, we jump out of the loop. So this is an example of one of the rules of the logic of Floyd-Hoare partial correctness, and there would be other axioms and rules for trying to capture other kinds of programming construct in the language. So there might be rules for if then else and for assignment and so on and so forth. And our intuitive understanding of what executing a while loop means enables us to, I guess, to say that this is indeed a reasonable rule. But unfortunately, things rapidly become much more complicated. So if we think, for example, of a language where, I mean, much more realistically from the modern point of view, it's very likely that if you're writing programs that are mutating the memory state of your computer, that you're going to have lots of concurrent threads of computational happening at the same time, and all mutating the state by individually, so they communicate amongst themselves by affecting the shared memory. So Cliff Jones added to Floyd-Hoare logic a more complicated form of partial correctness, where you make some assertions about the memory with regard to the various threads of computation that there are. So it, formally speaking, looks like this. So you have a component which is still the partial correctness. If C terminates starting with property P of the memory, then Q will hold of the memory when you terminate. But now that's only under the assumptions R and G. So R is a so-called rely assumption and G a guarantee assumption. And the intuitive idea is that R is some property that holds of the part of the memory that's only affected by threads other than the one that C is executing, and G then is describing part of the memory that's only affected by C. So then if we write down the rule for parallel composition of commands, so this command here is take C1 and C2 and execute them both in parallel, so that they affect the memory, the heap of storage cells as they go along. And here's Cliff Jones's so-called rely guarantee rule, and as you can see, it's pretty complicated actually. Oops. Sorry. Sorry about that. It's quite complicated. Let me just read you through it. So we're trying to execute two threads in parallel. So this part of it maybe is not unsurprising. We have some initial condition P1 that's relevant to C1 and some condition P2 for C2. So under the circumstances that both of them hold, then when we execute these two things in parallel, both of the post conditions Q1 and Q2 will hold. But that's only true if C1 and C2 interfere with memory amongst themselves in certain ways. And that's what these side conditions are saying, that the guarantee condition of C1 should be something that implies the rely condition of C2. And vice versa, the guarantee condition of C2 is something that's implying the rely condition of C1. So I think, and the point of me showing you this rule is not that you can understand it. I think it's probably quite hard to see why the rule is of the form that it is, and why it might be describing something that is correct about a programming language where there are concurrent threads affecting shared memory. So the point is that program logic rapidly becomes quite difficult to justify just by an intuitive reading of what you think things should mean. And we need to have some more low level, but still completely formal description of semantics from which we can then justify some kind of program logic that might be used in verifying software through the construction of proofs. In other words, it's not clear where such programming laws, as they're often called, come from, until we develop a slightly more mechanistic view of the meaning of programs, and that's what operational semantics tries to do. So again, I'll just give you a very brief flavor of one form of operational semantics. So you can imagine a situation sticking with a language where we're looking at a language of commands that are affecting memory states. So if we package a memory state and a program phrase up together, that kind of gives us an instantaneous snapshot of the state that we're in executing some program beginning with some memory. So an operational semantics might, for example, define a binary relation between such configurations. So how one step of carrying out the computation C gives you a new memory S prime, and what's the rest of the computation left at that point, the C prime. And operational semantics does that by defining typically relations like that. Again, a bit like with program logic, it's an inductive definition. You give some axioms and some rules for inductively generating valid instances of a relation of that kind. I mean, for example, sticking with a language where we've got while loops, you might well have an axiom that just says that when you have a memory configuration, some state S, and the phrase that you're trying to execute is a while loop, you can do one step of computation to unfold the while loop into this compound here, which is basically if the Boolean condition is true, then execute C and then execute the while loop again. And if the condition is false, then just skip out. In other words, become the command that does nothing. And then you would need to combine that with other axioms and rules, for example, to explain the meaning of if, as well as having axioms that say that, you know, if true, then C L C prime does a step to C, and if false, C L C prime does a step to C prime. You'd also need to have a rule like this that says, you know, inductively, if you know that your Boolean condition simplifies in one step in this way, then you know that a configuration where you've got an if then else simplifies in one step to something like that. So a typical operational semantics will define relations of this kind and similar relations. Is basically you have some what we call an abstract machine, so some piece of mathematical data that's describing the instantaneous state, not of an actual computing machine, but of some mathematical abstraction of it, and then relations describing how those states evolve, in this case through single steps of computation at a certain level of granularity. And for a very complicated programming language, it may be that the operational semantics itself is then, I mean, here we're talking about quite simple things, but in general, the language features can be quite difficult to capture, and there may be, you know, from the point of view of logic, rather a large number of somewhat arbitrary looking axioms and rules, but capturing how we want the machine to execute. If we're lucky, then the axioms and rules will at least follow the structure of program phrases. I mean, in this example, for example, we actually only have one axiom that explains the while loop, but it sort of does it recursively in the sense that the phrase reoccurs on the right-hand side of doing a step of computation. And here we have a rule that's sort of explaining something to do with if then else. So there's a so-called structural operational semantics, where at least the axioms and rules are driven by the structure of program phrases. However, this form of semantics and also program logic as well, the previous one, they both suffer from the defect of not really giving you a compositional explanation of meaning. And that's where the third style of semantics comes in, so-called denotational semantics. Its whole raison d'etre is to give you a compositional meaning, compositional explanation of phrases in your language. So at a very high level, a denotational semantics is going to be something where each phrase in the syntax of the language is given a denotation, so-called. So this will be an element of some mathematical object that represents the contribution of that phrase to the complete meaning of a program. So this is, I should emphasize, you know, I mean, it's with an operational semantics, you're writing down the definition of an abstract machine for executing whole programs. In a denotational semantics, you're trying to get at the meaning of phrases which in themselves are not whole programs that can be executed, but are constituent parts. And the ideal is to give that explanation by giving functions from denotations to denotations that you can compose together, that will give you the meaning of some compound phrase in terms of the meanings of its constituent parts. Let me just illustrate that, continuing with our a language where you have statements whose purpose is to mutate memory state, and maybe some expressions which are Boolean expressions about the state. So instead of, with the operational semantics, explaining how you can take single steps of computation, we could think about, supposing our language is deterministic, so there's a unique final state, if there is one, we could think of the meaning of statements in terms of functions from initial states to final states. They have to be partial functions because in general languages are going to be capable of expressing any partial computable functions. So ever since Turing and Church's work, we know that we can't cut down to totally defined computations without losing some expressive power. So in general, we're going to use partial functions to model denotation. So this hooked arrow here is just the set of partial functions, and I mean that partial functions, from the mathematical point of view, I mean just through their graphs, if you like. So they're sets of pairs which they're single valued, and oh, actually not total, that's a mistake. Sorry, I don't mean total, just single valued. So yeah. So we might aim to give a denotation to statements in our programming language as elements of this set of partial functions, where state is just some set of things some set of things that represent our different elements of the memories in the computer. And a Boolean expression then would be a partial function from states to Boolean values. Again, partial because it may be that Boolean expressions in the language involve executing statements in themselves, so they may not terminate on the way to telling you whether they're true or false. So, I mean, for example, some denotational semantics would be quite straightforward. I mean, if I wanted to give a denotation to a conditional phrase, and if then else, that would be relatively straightforward to do because I have some function that takes actual Boolean values and just gives me the first or second thing in the set of states, and I can compose that with the denotations for the phrases. So a typical denotational semantics will recurse over the structure of the phrases. So if inductively we've already got meanings for B and C prime, then the meaning of the if then else is given by composing with this conditional function. So in a sense, the conditional function is giving us the meaning of if then else. And in that case, because if then else is so simple, that's not very surprising. But in general, it might be quite complicated. I mean, if we take the while loop, for example, what's its denotation as a partial function from states to states? Well, it comes out as a least fixed point of a certain functional. So we have a function from partial functions from states to states to partial functions from states to states. So that takes such a partial function f from states to states and gives you another one. So then that will map a given state to this thing here. So this is taking f and applying it to the meaning of c and then wrapping that in a conditional. So it's equivalent to unrolling the while loop once, but we don't know what the while loop means, and f is standing for what it might mean. So if we take that function of f and form its least fixed point, so what is that? So it's a partial function from states to states that's fixed by phi. So phi of the least fixed point is equal to the least fixed point. And if you've got any other fixed point, some function f, partial function from states to states that's fixed by phi, then the least fixed point is contained in it. And the mathematics of domain theory, I mean, of partial orders, so we're part of that part of mathematics, provides a setting in which we're guaranteed to have such least fixed points. So again, it may not be immediately obvious why that's the right thing to do for a while loop, but one develops the properties of the denotational semantics and relates it to the operational one and the program logics, and that gives you some assurance that this is the right kind of definition. Now, the problem with denotational semantics is that programming language features rapidly become quite difficult to give compositional meanings to. And I just want to illustrate that with one example, which shows the direction in which the mathematics had to go in order to cope with that. So I want you to imagine we're still talking about some language where commands mutate state, but let's imagine that now that instead of just the state storing, you know, data like numbers or booleans, and indeed this happens in various languages, we have states where we can store bits of code itself. So we might, for example, have a memory state in which we store the definition of a method for computing with numbers to produce numbers. Okay, so to give a denotation to that kind of state, and also to expressions that involve mutating that kind of state, we might want to get a set E, which is partial functions from the denotation of states to numbers cross states. So in other words, we're thinking of an expression as taking an initial state and giving us a numerical result and a final state. And what's a state? Well, if we're allowing, say, one storage location to store a method for turning numbers into numbers, then if you think about it, S has got to be a partial function from numbers to this set E, which is the denotations of code, of expressions in this language. Okay, well, the thing is, I mean, if you put those two equations together, you can see that what to give a denotation of that kind of language, we'd be looking for a set E, which was equal to this set of partial functions. So it takes partial functions from N to E and gives you back things in pairs, a number and a partial function from N to E. And the problem with that is that there aren't any such sets, because I mean, if you look at the right-hand side here, you can see that if you just what would be the cardinality of such a set, it would be at least the number of subsets of E. And we know from Cantor that that's a cardinality that's strictly greater than the number of things in E. So there is no set which satisfies this equation that we could use to give denotations to that kind of language where we have a memory cell containing a method for computing on numbers and giving numbers. And indeed, I mean, here I've asked for this equation to be solved up to equality, but you could loosen that and ask for a set E which was in bijection to this, and that still, of course, wouldn't be any good. There wouldn't be any such sets. So denotational semantics had to devise ways of getting around that kind of problem, which arises all the time. It arose, historically speaking, very early on. People were interested in something called the Lambda Calculus, which is a notation for describing functions, and the untyped Lambda Calculus was used, in fact, by Alonzo Church in his original work on computability to prove the undecidability of the halting problem. So at the same time that Alan Turing was devising his notion of thing that we now call Turing machine. And it took a very long time for mathematicians, Dana Scott in particular, to devise a way of giving a denotational semantics to the untyped Lambda Calculus, because it did involve exactly this kind of problem, that a set of denotations of lambda terms would have to be in bijection with its own exponential, and there are no non-trivial such sets. So it seemed very hard to give a model of semantics in set theory to the untitled Lambda Calculus. And the solution was to work not in sets, but in other kinds of category. And in fact, that's where category theory enters the picture. So category theory is a branch of pure mathematics that studies the structure in various kinds of mathematics, not through building the structure up by saying what elements a structure has and what relations there are between those elements, but actually saying how one structure transforms into another one. So that category theorists talk of the notion of morphism. So it's a structure preserving transformation. And a category is nothing other than a collection of similar structures with the morphisms between them. And it's amazing what can be described in mathematics from that point of view, rather than from the sort of usual set theoretic elements and element theoretic, as it were, point of view. And it's been a particularly useful thing for computer science and for denotational semantics in particular. Because instead of trying to solve equations like that in the category of sets and functions, we can move to other categories, typically ones that have some kind of topological aspect to them, or originally it was through various order theoretic structures that come to be called domains. But the idea being that you have fewer transformations around preserving the structure, and so this cardinality property is kind of avoided in that way. I mean, there's more to the story than that, but that's at least one aspect of it. So denotational semantics has used various kinds of category theory in a big way in order to even get something where you can give a compositional explanation of some particular kind of programming language. Okay, so those are three styles of programming some language semantics that one sees. I just want to spend the rest of this talk, I want to compare them by addressing what's a pretty fundamental question, really, which is what does it mean for two parts of a program, two program phrases, to actually be equal? So what does equality mean for programs? I mean, obviously one answer would be if they're literally the same pieces of syntax, but that would be a rather boring answer. What we want to have is a notion of equality where equality means that they have the same meaning and have the same semantics. And the three different styles come up with different answers to what that notion of equality should be. So for program logics, it's going to be that two phrases are equal if basically they have the same derivable properties in the logic. So you might say that two phrases in some language for mutating state, where you have a Floyd-Hoare pre-post condition sort of logic, would be equal if whenever one assertion in Floyd-Hoare logic is true of C, then it's also true of C prime and vice versa. So that's, I guess, a reasonable answer to equality if you're basing your semantics on some kind of assertions about the behavior of programs. Denotational semantics is pretty straightforward. In denotational semantics, we're giving a meaning to program phrases as elements of some mathematical domain. And so it's natural to say that two phrases are equal if they have the same denotations. But the one that's least obvious, I think, is the form of semantics which is the easiest to do, the lowest level one, as it were, operational semantics, where you're just formally describing some abstract machine for executing programs. And there, at least one answer to what programs mean is the notion of contextual equivalents, so-called. And let me explain what that is. So one would say that two program phrases are contextually equivalent. So we assume now that our programming language comes with some operational semantics as part of its definition. So I have a notion of what it means to execute whole programs. But if I have a part of a program, you know, a subphrase of the program, what does it mean for that phrase to be equal to another one? So contextual equivalence would say that they're equal if, when you interchange the two phrases in some complete program and executing that program, you'll get the same observable results whether you use the first phrase or the second one. So this does depend on not just having an operational semantics, but also on agreeing what it is you're going to observe of executing programs using the operational semantics. So, and different choices of what you observe may very well lead to different notions of equality. So I would say that this, you know, so this is computer scientists rediscovering something which I guess one could say goes all the way back to Leibniz with his identity of indiscernibles, you know, which says that two mathematical objects are equal if there's no test to distinguish them. Excuse me for my translation from the French, I think, was it, that Leibniz wrote in. So the principle of identity of discernibles is you know, one reading of it is it means that. And here we're sort of applying that kind of principle where we're talking about not mathematical objects, but phrases in some programming language, and the test to distinguish them is observing results through using some operational semantics that we begin for the language. In computer science, the notion arose, I think, first in the 60s with the PhD thesis of Jim Morris, so who I think probably was not at all aware of any kind of philosophical connections with Leibniz, but just wanted a good notion of program equality for languages like Lisp based on Lambda Calculus. So contextual equivalence is actually quite interesting. I mean, it's in one sense, it's philosophically interesting, I would say, because it's something that arises through the operational behavior of programming languages. So it's not part of mathematical logic in the sense of that a logician would understand proof theory or model theory or recursion theory, because those people wouldn't start with an operational semantics of the programming language. So it's appealing because it's distinctive, I guess, to the subject that I'm telling you about. But it's also pragmatically very important because very often the easiest way to proceed in program verification is to devise an operational semantics, and then one wants to prove consequences of that definition, and contextual equivalence is a very big part of that. I mean, obviously there are properties of programs which aren't in the end just to do with the quality of one phrase with another, but nevertheless this is an important and useful part. But it's also quite difficult part because this quote I had from John Reynolds about combining language features, giving you counterintuitive interactions, and that's very true, I think, for operational semantics and contextual equivalence. Just to give you an illustration of that, so there's a class of programming languages that some people will call hot. This is a kind of stupid acronym, but the H stands for higher order, HO, higher order, and T for typed. So these are languages where you can write programs which describe functions, and maybe functions that take functions as data, first-class data, and they probably have various fancy typing features as well to do with polymorphism, and that might be combined with ways of structuring state in terms of, say, object model, and indeed it might be combined with various ways of executing things concurrently. So that combination of features is quite tricky. there are lots of languages that have those features, but they lead to quite difficult interactions. Let me just try and give you a flavor of that. I've written on this slide just two little program phrases from a language called OCaml, which is quite widely used, but I don't expect you probably have come across. Let me just explain kind of in general terms what these phrases are doing. So this is in this phrase, these are both phrases that are trying to define a function from numbers to numbers. Okay, so it'll take in a number x and produce a number. And in the first case, what it does is it takes in a number x, and then it mutates a little piece of memory that it's created in which it's stored the number n. N is just some identifier for some unknown number. So first of all, it increments the store by adding the argument x to what's already there, and then it returns the contents of the store. So when you use this, you create a fresh memory cell A, and then you return a function that maps x to this piece of code that adds x to the state A, which starts initially with the number n in it, and returns the value that's stored there. So what this phrase does is something similar, but it just puts lots of negatives in. So it stores minus n initially in some memory cell B, and then it returns a function that sends y to subtracting y from the memory cell, and then returning negative of the contents. So if you think about it, those two phrases are probably interchangeable, because you've inserted negatives kind of uniformly through. So you shouldn't really be able to observe a difference between using this phrase and that phrase. And that's in fact true if one has an operational semantics for OCaml. We can look at using these two phrases in some complete context that becomes a program. You see, I mean, they're not themselves programs, because this n is just an identifier. So you can't really execute this until you know what n is. But we might use that inside a program where n is bound to some particular number. So a context that sort of closes off the dangling identifiers. And it is indeed the case that whatever context we use, we'll get the same behavior. Say, we'll observe the result true, whether we use h or we use k. So that's kind of maybe what we'd expect. But then you can do more complicated things where maybe what you expect doesn't hold. I mean, so here I've written a function. This is a function that takes in the names of memory cells and gives back the names of memory cells. So not numbers to numbers, but names to names. And a picture of what the one on the left does is something like this. It creates two private names, A and B, and then as a function, it inputs a name and returns the name A, whereas inside the sort of private world that it's created with A and B, it just interchanges A and B. On the other hand, this one, what it does is it creates private C and D, which it maps C to C and D to D, and when you return the function, if you supply some argument y, it'll just map that to C. So it looks like these are probably going to be the same, because from an external point of view, it's just a function that takes in a name and gives you some private name, the identity of which is sort of not known to you because it's private. And that's true both of the left-hand side and the right-hand side. And inside the sort of private box, you can't see exactly what is going on. So from the outside, it looks like these are basically equal things. But appearances can be deceptive, and in fact, in this case, they are distinguishable. So one can devise a program which basically can detect that different things are going on inside this private box, even though it doesn't have access to the actual names A and B. It can devise a test, namely applying the function to itself twice and once and comparing results. And that would allow us to, in fact, write a program in which if we used F inside the program, we'd get false. And when we use G inside the program, we get true. So these are not contextually equivalent things. But in a sense, non-contextual equivalence is quite easy to prove because you just have to give an explicit demonstration that you get different observable behaviors. Whereas the positive one, the one that was somehow easier to see might be true, is actually harder to do because we have to somehow prove something about all possible closing contexts. And so that's not very easy to do directly. And a lot of effort has been expended on devising methods for proving contextual equivalence by developing various kinds of mathematical approach with so-called logical relations and things like that. Okay, so getting towards the end. So there are these three styles of programming language semantics, and they have the different pluses and minuses. So programming logics are very often used for the important task of software verification. And you can validate, you know, they get complicated, but you can justify the axioms and rules by maybe relating the program logic to a more low-level thing or to denotational semantics. Denotational semantics, you know, is more foundational and it involves quite sophisticated mathematics and category theory. But if you can do it, you learn a lot about the underlying meaning of the kind of computational constructs that you're trying to use in your programming language. Whereas in the middle, operational semantics has sort of become the workhorse of programming language semantics in practice. It's the easiest one to devise, but it's also in some sense the hardest one to use. So because there's no free lunch, as it were. Okay, so I've got a couple of minutes left. Let me just mention where things have gone. I've mostly talked about things which are historic in nature, so things that arose during the development of programming language semantics. Where is the subject at the moment? One place it's at is, and I'm thinking now from a kind of mathematical, philosophical point of view rather than just a practical one, is a lot of programming languages originally were programming functions, in other words, input-output. But these days, of course, software, you know, contains a lot of concurrent activity going on through threads or through processes communicating with each other. And we have operational semantics for these things, but we don't really have an analog of the Church-Turing thesis. In other words, some convincing reason why all of these different operational models are in some sense equivalent to each other, or give you computationally the things that are equivalent. And that's because really there isn't at the moment a completely convincing denotational model of the notion of concurrent interaction between communicating processes. So we don't really have a very good answer for the question mark in this proportion. I mean, so in ordinary deterministic IO computation, the set theoretic static notion of function is basically you know, denotationally what's being used. May be qualified in some ways, but we don't, as it were, have the analog of that. At the moment, probably the best thing that we do have, people use certain kinds of two-player games and they model computation through winning strategies for various kinds of games. And that's gone a long way to giving a high-level view of interaction. The interaction being the reason for two players is you could think of the two players are the process itself and its environment and the interaction between those two things. So that's one thing. Another thing is on the slightly more pragmatic side of software verification. You know, we've gone from the 60s to the 2020s developing these kinds of operational denotational programming logics, and But it's sadly still the case that when a new programming language comes along, it almost always comes with a completely formal definition of its syntax using formal language theory, grammars, and so on. And it might come with a natural language description of what it's supposed to mean. And it'll, of course, come with an implementation, because otherwise nobody would be able to use it. But it doesn't at the moment very often come with a precise formal mathematical definition of its semantics. And we really, because programming languages are often quite large artifacts, we really do, and the software that's written with them even larger, we need better tools for managing definitions and proofs, especially in operational semantics. So let me finish just by, if you're interested in reading more, I have 3 suggestions for you. And actually the 3 suggestions have to do with what's going on to meet this opportunity of providing better tools. So these are 3 books. They're all online, so you can read them online, about programming language semantics, but they all use interactive theorem proving tools in order to allow you to understand the mathematics and to prove things about it. So Benjamin Pierce and many other authors have a series of volumes on software foundations, and they use the so-called Coq theorem prover from INRIA in Paris. And that actually is being used to train whole generations of graduate students in programming language theory in North America now. So there's a generation of people emerging who just think it's natural to use a machine-assisted theorem prover in order to develop things about software. Phil Wadler and his co-authors kind of took this work and turned it into one using the AGDA theorem prover, which happens to be the theorem prover I most like using, and that's quite a nice readable introduction to programming language foundations. And a somewhat different kind of theorem prover, the so-called Isabelle Hole theorem prover. So that uses Church's higher order logic, whereas AGDA and Coq use Martin Löf's dependent type theory as a foundation. But this is also a very nice book. So there are places where one can go and read if you're interested in. But I think I'll stop at this point, and thank you very much for listening.